behalf of RBCS and software test professionals, we welcome everyone today to this webinar on advanced software testing code coverage. I'm Rex Black. I'm president of RBCS. We are a worldwide testing and quality assurance firm serving clients that range from small startups to Fortune 20 global enterprises. Since 1994, 17 years ago, RBCS has been both a pioneer and leader in quality hardware and software testing. We are based in the United States with partners around the world. We deliver insight and confidence to our clients. We help them get quality software and hardware products to market on time and with a measurable return on investment. We have a team of international consultants that deliver customized training, consulting, and outsourcing services for companies that are looking to improve their test and quality assurance practices. RBCS has helped hundreds of companies reduce development and support costs while assuring the best quality products are delivered to customers. I'm the author of Pragmatic Software Testing, Advanced Software Testing Volumes 1, 2, and now 3, Foundations of Software Testing, Critical Testing Processes, and Managing the Testing Process. I hold a degree in Computer Science and Engineering from UCLA. And I'm the past president of the International Software Testing Qualifications Board and the American Software Testing Qualifications Board. We are presenting this webinar today in partnership with software test professionals. In addition to our ongoing collaboration on webinars and training, I will be the opening keynote speaker at the Software Test Professionals Fall Conference on October 25th in Dallas, Texas. Hope to see each of you there. In addition, if you haven't visited their association website, check it out. It's www.softwaretestpro.com. That's softwaretestpro, P-R-O, all one word, .com. Now, before we start the presentation, the usual housekeeping notes here. If you have any questions at any point during the webinar, you can submit them. Your webinar interface has a Q&A feature on it, so you can submit your questions, and I'll be answering those at the end during the Q&A session. You do not need to ask for presentation copies. The presentation is on the web. It's at www.rbcs-us.com, and what you want to do is go to the Resources tab and navigate to the Basic Library, and you'll find it there. There's also no need to ask about how to register for the free e-learning. Simply by attending this webinar, you are registered automatically. Check your email over the next couple days and watch the spam filter to make sure the notification doesn't get lost in spam. You do have a limited amount of time to respond if you are the winner. If you are having problems with either the audio or visual components of this webinar, please contact GoToWebinar support. If for whatever reason you cannot get to the webinar online, or if you're dealing with an unreliable connection, download the slides from the Basic Library, as I said, rbcs-us.com, go to the Resources tab, the Basic Library, find the slides there, and then you can use a telephone to connect rather than voice over IP. But this doesn't really happen very often. Do have the most frequent problem that people have, which if you're hearing my voice you don't have, is that their software firewalls block them from accessing GoToWebinar events due to corporate policy. If you are having problems, then there's not much we can do about that other than getting your policy changed. The other problem that sometimes people have is browser incompatibility. We've heard reports of the latest version of IE being incompatible. So if you're hearing my voice but not seeing the slides, the thing to try would be to try a different browser. Hope you enjoy this free webinar from RBCS. We do these free webinars as a service to the software testing community because at RBCS we're a not-just-for-profit company. So today's presentation is on code coverage metrics, how to understand them. There's a lot of newfound popularity of code coverage metrics, thanks in large part to the Agile techniques. A lot of the tools, many of which are free, that are associated with Agile and unit testing for Agile have capability to produce code coverage metrics, but we see with our clients a lot of confusion about what do these really mean. Just at the technical level, what is it telling me about what's not tested and not tested in the code, and then also at a confidence level, what is it telling me in terms of how much confidence I should have in the tests that I've run. So the point of this webinar is to help you understand these most common code coverage metrics and apply them properly in your day-to-day work. Material in this webinar is adapted from my newly released book, co-authored with Jamie Mitchell, Advanced Software Testing Volume 3. Okay. That book is designed for people in a technical role, technical test analysts, programmers, test engineers, test automation people. And in that book and in this webinar, we're focused on sort of going beyond the black box techniques to say, well, let's look at what we have and haven't tested in our code, and then think about, does it matter? What we haven't tested, does it really matter, or are we okay with not testing that? Now, this should be seen as complementary to the black box techniques, which are very useful for checking the proper behavior of systems. It's sometimes referred to as behavioral testing. And it's also white box techniques complement static analysis, which is done often looking directly at the code with various commercial or freeware tools to try to look for certain kinds of defects, especially things like maintainability, defects, problems with security weaknesses, bad variable names, unreachable code, and so forth. So these white box techniques should not be seen as replacing those black box and static techniques. They should be seen as complementary to them. Now, specifically, what we're going to look at here is the type of code coverage metrics that you're most likely to run into, which are those related to control flow. Now, there's also another category of code coverage that we could look at called data flow, but we're not going to get into that. Most of the tools that you're going to run into, most of the tools you're going to see are going to focus on control flow coverage. So there are various different levels of coverage, and we can talk about statement coverage, which is sometimes referred to as instruction coverage, or confusingly code coverage. I saw one open source tool which certainly looked like a very useful tool, but it was kind of confusing in the way that it talked about code coverage in the sense of statement coverage. But I think more properly, code coverage refers generally to all of these type of control flow and even really potentially data flow coverage metrics. So don't be confused by that. But anyway, if you see a statement coverage, instruction coverage, or code coverage in the sense of distinct from other types of white box coverage metrics, then what's meant by that is that every statement in the module has been executed at least once. If you have 100% statement coverage, that's what it means. Every executable statement has been executed. Might have been executed more than once, might have been executed thousands of times, but for every statement you can identify at least one test that ran through that statement. Now, another level of coverage is what's called decision coverage, or it's also referred to as branch coverage. These are the same. So if you see these in a tool and it's talking about branch coverage or it's talking about decision coverage, it's talking about the same thing. Again, if it's using the phrase code coverage and then it's also using the phrase decision coverage, the distinction is that code coverage that they're referring to is what I'm calling statement coverage here. Decision coverage means that every decision has been tested for both outcomes. So if you've got a if statement, then the if statement is driven by a conditional expression, and that is going to evaluate to true or false. And basically, decision coverage means that it's been done both true side and the false side, which is also a way of thinking from a branch point of view. If we draw a diagram, we can see, okay, it's a branch that exists here where the control flow can go one way or the other. And that means that all of those branches have been taken. Then we have what's called condition coverage. Whoops, I apologize. I've had a technical problem here. Let me just get this cleared up. Yeah, there we go. So condition coverage, now we're going to look at the conditions that make up the decision. So you've got an if statement, a while loop, all of those things, for loops are controlled by a conditional expression. And so in condition coverage, we're looking at the conditional expression in detail. Now, there are a lot of different variants of that, so I'm going to explain the different variants. You have to be real careful about what kind of condition coverage you're talking about when you're looking at discussing condition coverage, because there are many variants and they mean very different things. Then you can sometimes see what's called multiple condition coverage, which is every possible combination of outcomes of the different individual conditions. This is a very high level of conditional coverage, which I'll explain here. So let's go through and look at each of these different types. So we'll start with statement coverage. Conceptually, basically what we're saying is that if we want to achieve 100% statement coverage, what we want to do is make sure that our tests are designed in such a way that every executable statement has been executed at least once. And to the extent that as we run our tests and we find that there are still executable statements that have not been executed, then we are going to add some additional tests or test data to try to force those statements to be executed. And we're going to repeat that process until the number of statements executed divided by the total number of executable statements is 100%. Now we can also we could set the target lower than that. It's kind of difficult for me to understand why you would want to have untested executable statements in your code, but there can be certain circumstances where you've got, say, exception handlers or something like that that are just so completely obscure. They're basically there as the kind of this should never happen handlers. You can't figure out how to make it happen, but you want the software to be safe if it does. I think that's a possible exception to the rule about getting to 100% statement coverage at the very least in unit testing, but that would to me seem to be about the only really justifiable exception to that. Here's an example. This is a very simple little piece of code that uses a for loop to calculate a factorial. So what it's going to do is it's going to let me get the highlighter up here so I can point out what's going on with this. So it comes in, it declares its variables, it puts a prompt up on the screen asking you to enter here, scanf, the number that you want a factorial of. And then what it does is that if the number is less than 0, that's invalid, so it gives you an error message. It sets n to be equal to -1, which is apparently the error code that's returned, and then it's exits out of that block and comes here. If n is greater than or equal to 0, it goes here, sets f equal to 1. The factorial of 0 is 1. And then it goes through a for loop 0 or more times, multiplying f times itself there. What we're going to do then is when we exit the for loop, it's going to print out the factorial value here. So it's going to say n, so factorial of whatever number you give is this, and then it returns n. Okay, so we can, if we test with n less than 0, say -7, we will come here, and if it's from a diagrammatic point of view, you can see we're going to do the red side of this diagram, right? See, this here represents this if statement, right? We can branch off that way, which is this code here, lines 8 and 9, and then 17, and we exit. And then if we test with n greater than 0, say 5, come in here, go in here, here, go, okay, so f 1. Now we're going to go around the loop 5 times. So it's 1 times 1, and then 1 times 2, and then 2 times 3, and then 3 times 4, or well, 3 times the factorial of 2, excuse me, and then so forth until we've iterated around this loop 5 times, accumulating up the factorial of 5, which is 2, 6, 24, 120. And then come down here, we're going to say 5 factorial is equal to 120, and then exit out. Okay. So notice that every executable statement has indeed been executed at least once in this with those 2 test values. So that got us to 100% statement coverage. Okay, so now decision coverage. Decision coverage, we're going to move up a level, and we're going to say, you know, not only do we want to make sure that we cover every statement, we actually want to look at the control decisions, because that's really what's driving control flow, right? I mean, it's you get there and you say, okay, well, I'm either going to do this or that, right? If this is true, do this chunk of code. Otherwise, do this other chunk of code. So we want to make sure that there's data that will force every decision to be evaluated both true and false. Now, what we do is we look at the tools. Not really the tools are going to do this for you. The tool, when you look at it, a tool that's saying you achieved 75% decision coverage, well, the tool is calculating that because it knows, based on parsing the code, how many decisions there are, and it knows how many of those have been executed, because they use what's called instrumentation to track what's been executed and what hasn't. So what we're looking for here is a situation where, because a particular decision either has or has not been taken, that leads to some kind of problem in the code, oftentimes like after the decision either is or isn't taken. The classic example of a bug that can be revealed by going for decision coverage is where you get a if statement where in the block of code on the true side of the if statement, some sort of precondition is created, and then after the if block, there's a chunk of code that assumes that under all circumstances that precondition has been set. For example, a variable that's been initialized. But actually, that variable has only been initialized in the case that the if statement evaluated to true. If the if statement evaluated to false, the variable would not have been initialized. And then when you try to use the value in that variable, if the decision has been actually false rather than true, you'll get some kind of error. That's sort of the classic example of this, and that's what we're going to try to avoid. So going back to our factorial program example, you see that before, to get statement coverage, remember we tested with -7 and 5, right? And in 5, you actually do iterate the loop 5 times here, right? Let's get the spotlighter back up. If n is 5, we iterate the loop 5 times. But we don't ever try not ever doing the body of the loop. So if we want to get decision coverage, we want to test what happens if this loop body here, this chunk of code, doesn't ever execute. We would also check with test with n equal to 0. So if we tested with -7, 0, and 5, we would check. We would test that, and we would cover that condition. Now you might say in this case, well, geez, who cares? Well, here's why this could matter. Okay, let's suppose, let me get the highlighter up. Let's suppose that this statement here, this f gets 1. Instead of putting it there, let's say that the programmer is clever. The programmer says, I'm going to say f gets I gets 1, right? Which is a legal statement because I gets 1 evaluates to 1, right? So now we're going to be clever. We're going to initialize f and I to 1, same time with a single statement in the beginning of the loop control variable. And then we run this code. Well, if the block never runs, what happens? Well, F does get initialized into 1, and it works properly. It looks funny, but it would work properly. It would read very oddly, on the assumption that the loop control variable, of course, is set prior to the evaluation here, which indeed would have to be. Let's suppose that instead, what we rewrote this in some way that it was like a do-while loop or something like that, right? Where the printf was inside the body of the loop. Now, if that were to happen, then it would be possible for the program to work correctly for everything except 0. Because if it got to 0 and the body of the loop didn't execute, then you wouldn't get a printf. So that's one example. Now, but the more classic example would be, let's say that we had a pointer. We declared a pointer variable up here, and that pointer was initialized in here. Let's say we had a statement in here where that pointer variable gets initialized, so point at F or something, and we return a value, or we try to use a value in that pointer here, or maybe down here. Well, in that case, that pointer would not be initialized, and you would then try to dereference a null pointer when you tried to access it, and that's the kind of thing that would then result in sort of abnormal termination, typically, of the program. So that's the kind of bug we're trying to avoid here. We're trying to avoid a situation where something needs to happen for everything else to work normally. The assumption has been made that, oh, that will always happen, that precondition will always be satisfied, but in fact, it's only satisfied under certain decision situations. Okay, now another thing which you might run into in the tools is loop coverage. This is a little more obscure, and not all the tools are going to have this by any means, but you might see it. Now, what are we talking about in terms of loop coverage? Well, anytime you've got a loop, the number of times that loop can execute can be very large, possibly close to infinite. You're not going to test every possible number of times the loop could iterate, and the value of doing that, of course, would be extremely low, because it just doesn't make sense to think that there's a loop that can execute 10,000 times. Is there really any value in testing it running 5,000 times and 5,001 times? I mean, what's the likely difference? Yes, we can posit a bug that would happen exactly at that point, but maybe that bug would also occur if we tested it the maximum number of times. So that's what you're usually going to try to do is force the loop to execute 0 times. In other words, the body of the loop is never done. Execute exactly 1 time, and then execute n times, where n is ideally the maximum number of times that the loop can execute. Now, in some cases, that maximum is not possible, either from a practical point of view or from the point of view of there really isn't any maximum. The system is supposed to stay up forever. It's supposed to go around in this loop processing input indefinitely. So that can be the case. And in that case, you just have to identify a number of iterations of the loop that is sufficiently large that you are confident that if there were problems associated with doing the loop a really, really large number of times, you would find it. What kind of problems are we talking about? Well, running out of memory, for example. Let's suppose that there's sort of memory allocation going on inside the body of the loop. We might well be concerned that that's going to run out. So let's take a look at our factorial example here. So we did in our testing of testing with 0 and testing with 5, we did test 0 times. Now we would have to test with n being set equal to 1 here. Get the spotlighter again. So we'd have to set n equal to 1 to get to do it 1 time. And now in terms of the maximum, well, you know, I mean, theoretically, there's no real maximum in terms of, you know, any integer is a valid input for a factorial calculation. So we could pick some really enormous integer, but you actually would not have to pick a really enormous integer to find the bug in this program. If you test it with something as little as, say, 50, which is not an enormously large number of times for a loop to iterate, but in this case, that would reveal the fact that you would indeed overflow the integer value, the f value, and you would go from an increasing factorial number as you put larger and larger numbers in, to all of a sudden it would wrap around and become negative. And that would reveal the fundamental flaw in the implementation of this program, which is that 32-bit or even 64-bit for that matter integer is probably not going to be sufficient to do anything particularly interesting from a factorial point of view, unless you want to set the maximum to be some really low number. Okay, so let's look at condition coverage. Now this is where, if your tool gives you condition coverage, this is where this can get a little bit hairy. Statement and decision coverage are straightforward enough, but condition coverage, that can be confusing. So if we're talking about just basic condition coverage, and we're going to, as I said, we're going to look at some other variants of condition coverage. So you have to be sure, if you're looking at a tool and it's talking about condition coverage, you want to be sure that they're talking about exactly what I'm talking about here. What I'm talking about in terms of condition coverage here is that every atomic condition, which is as it says at the bottom, the simplest form of code that can result in a true or false outcome. I'll show you some examples of that. Every atomic condition has been evaluated such that each atomic condition has been at least 1 time true and at least 1 time false. What we're going to do is, if you're trying to get condition coverage, is you're going to look at that condition coverage and you're going to look at the conditions that haven't been both true and false and force them to take on the value, either true or false, that they have not yet taken on. Now, a tool that is calculating condition coverage, the way it's going to do that is it's going to say, it's going to parse the code, and it's going to know the number of Boolean operand values that have been taken, or the total that exists, excuse me. And then as you're running your test, the instrumentation is going to keep track of which values have actually been taken on. So it's going to take the number that's taken on divided by the total number of possible outcomes. So just a simple example, if we have a single Boolean variable, and that can evaluate, when I say Boolean, by the way, I mean the same as logical, right? Can be either true or false. So we have a single Boolean variable, can be either true or false. If it's only been true, then for that variable we've gotten 50% condition coverage. And if it's been both true and false, then we've gotten to 100%. Now let's say that we have 2 Boolean operands, and one of them has been both true and false, and the other one has only been true. In that case, we have 75% coverage. We've got 2 plus 1 is 3, right? But we've got 2 plus 2, 4 possibilities there. Okay, so let's look at this a little more closely. Now first, I would point out that the decisions are made by looking at atomic conditions. Now, there can be 1 atomic condition, or there can be multiple atomic conditions. And the multiple atomic conditions can be combined through either logical operands, ands and ors, or we can have also relational operands where things are greater than or equal to, less than, so forth. Okay, so first example here, let's get the handy-dandy spotlighter out. We've got a Boolean or logical variable x, which can be either true or false. So in that case, there's a single atomic condition. Okay, x is either true or false. Now here we have two logical or Boolean variables, d, f, and we're combining them together with the logical operator and this can look a lot different depending on what language you're working in, right? But it's very common notation here. So d and f. So there are two atomic conditions that are being combined with a logical operator to take a decision. So if d is false, then d and f will be false, or if f is false, then d and f will be false. Both d and f are true, then d and f will be true rather than false. Now here we can say, okay, we've got a and b. Let's say that these are Boolean variables that are either true or false. Then we have c and d, and let's say these are integers. So now what we've got a logical, an atomic condition here, because this can be either true or false. Atomic condition here. They're being combined together with this OR operator here. And then we have C and D. Now notice that those do not take on true or false values by themselves, right? The result of this relational operator here, this equals, is what is going to say, okay, this C equals D, that's either true or false. So that's the third atomic condition, and those combine together to lead to some sort of decision. So if A is true or B is true, either one of those, A or B is true, and C and D are equal, whatever those are, then the condition will evaluate to true. If both A and B are false, then this will evaluate to false. Or if one of the two, A and B are true, but C is not equal to D, then that will evaluate to false. And then here we have A greater than B. So this A, B, these are integers or floating points or some other sort of value that's ordered value. So there's an atomic condition. Right? And we got x plus y is equal to -1. So again, we see a logical operator here. It's combining two non-Boolean or non-logical values. In this case, we have a constant and we have an arithmetic expression. And then we have, again, this is another relational operator is not equal true. D is not equal to true. So that's your third atomic condition, right? Opposed to this relational operator. Now, those are combined atomic conditions, each of which results in a single decision, true or false. Okay, so again, going back to condition testing, and in condition testing, we want to say that each atomic condition has been evaluated true or false. So simple condition testing, condition coverage, all you have to do is make sure that X, D, F, A, and B were at least once true and once false. And then C equal to D, that would have to be true once and false once. A greater than B would have to be true once and false once. X plus Y equal to -1 would have to be true once and false once. And D not equal to true would have to be true once and false once. That's going to get you condition coverage. Now, turns out that that's actually pretty simple to do and is weaker than, say, decision and even statement coverage. You could conceivably get condition coverage, as explained on the previous slides, and without actually achieving decision coverage or even statement coverage, which is problematic. So sometimes you'll run into something which is called decision condition coverage. And basically what that's going to do is that's going to combine the rule for decision coverage with the rule for condition coverage. It's going to say that not only must each atomic condition be evaluated once true and once false, at least once true and at least once false, we also want to make sure that we achieve decision coverage. So what we're going to do then is look at did we get basic condition coverage and did we get decision coverage? So look at an example here. Okay, so we have if A and B. So let's say that A is a logical variable, B is a logical variable. All right, if A and B. So if we test, notice that if we test with A is equal to false and B is equal to true, and then A is equal to true and B is equal to false, that's sufficient to get us condition coverage. But notice that this overall logical expression here, A and B, will have been false both times. So you'll not have done the body of the loop, true body of the loop. Okay, we don't necessarily like that. So if we then say A true and B true, and then those will both be true. Now, you might be looking at this and saying, well, okay, I see three tests here where A is false and B is true. A is true and B is false, and then A is true and B is true. Couldn't I also just test with A is true and B is true, and A is false and B is false, and then I will get both condition coverage and decision coverage, or decision condition coverage, with two tests? Yes, that is absolutely true. You could do that. So don't look at this and say, oh, it's necessarily the case that getting decision condition coverage is going to require more tests than just getting decision coverage or just getting condition coverage. That's not necessarily true. It depends on how the tests are designed. Now, is that sufficient? Well, kind of depends. Not if you're testing airplanes. So the U.S. Federal Aviation Administration, or FAA, has a standard, DO-178B, that requires a level of coverage called modified condition decision coverage. You might run into this. Might be, if you're using test tool, you might see this, MCDC. You might be saying, well, MCDC, modified condition decision coverage. What does that mean? Well, basically what that is every atomic condition has to be evaluated both ways, true or false. That's condition coverage. And we have to get decision coverage. So again, that means that every decision has to have been evaluated once true and once false. We just saw that condition coverage does not necessarily imply decision coverage. So this is adding a higher standard. And there's a third piece to modified condition decision coverage, or MCDC coverage, which is every condition has to affect the outcome decision independently. So in other words, we have to be able to identify a test where had one of the conditions been different. In other words, one of the conditions is evaluated to false instead of true, or true instead of false, that would have changed the overall decision from either true to false or false to true. Okay, now I'm going to show you an example of that, because this is the part that people often have a little difficulty getting their head around. So if you look at the DO-178B standard, what does it say? You've got an MCDC coverage. Then every decision has taken every possible outcome, true or false. Okay, that's straightforward. Each condition takes on every possible value, true or false. Okay, that's straightforward. Each entry and exit point is invoked. That means that every function has been entered, basically. Which, this is statement coverage, really. saying you have to have achieved statement coverage, because what we're saying is that if you have a function that doesn't have any decision points in it or any conditions in it, then that still has to be tested. And then the fourth thing here, as I said, each condition in a decision independently affects the outcome of the decision, assuming that the other conditions didn't change. Okay. So we'll look at an example here. Now one of the things that comes up with MC/DC test coverage that can be a little bit tricky is when you have what's called short-circuiting. Now, I'm not going to have time, and nor do I think it's really appropriate to try to go off into a lengthy discussion about short-circuiting and how it works. But basically, a lot of compilers have the ability to, when they're evaluating a compound logical expression, that if they can get to the point where all of the other conditions in the compound expression don't matter, don't have to evaluate those, the value of the expression is already determined. It stops evaluating the expression. So the simplest example is if you look at this statement here. Let me get the highlighter up. If A or B. Okay. Now, in the case, if A is true, then whether B is true or false doesn't matter. This is going to be true. This compound condition. So a short-circuiting compiler will generate code such that if A is true, then it does not look at B, doesn't evaluate B. And that does have some interesting intersections with MC/DC coverage. I don't want to go into gory detail on that, but it's a caveat that you need to keep in mind as I walk you through this example, because if you're dealing with a short-circuiting compiler and you're trying to get to the MC/DC, 100% MC/DC coverage, you could run into some problems. Okay, so based on this information, let's look at this example here. Examples will be helpful in this particular case. If A or B, so that's A, B, and C are Boolean variables, logical variables, let's say. So if you have A or B and C, then something happens as a code block here, okay? So now we can get decision condition coverage. We say A is true, B is true, C is true. A is false, B is false, C is false, right? You see that A, B, and C is each taken on a true value and a false value, at least once. And the decision has evaluated to true once, and it's evaluated to false once, okay? So we've gotten decision condition coverage. But here's the thing. B has never actually affected the outcome of the decision. See that? So A is true, no matter where B is true or false, right? False or false. Okay, now here you might say, well, if B were true in this second case here, if it were false, true, then this would be true. Yes, but since this is an and C is false, B still doesn't change the decision. If this were an or, then changing B to true would indeed affect the decision. But because this is an and operator here, changing B in either one of these test cases won't change the outcome. You see that? This is, if I said A true, B false, C true, I still get true. And if I say A false, B true, C false, I still get false. So B has not been able to independently affect the outcome of the decision. And that's the problem with that pair of tests. That's why it does not get MC/DC coverage. Hopefully that's clear. If it's not, we can come back to it during the Q&A session, because that independently affecting the outcome of the decision part is where people get really hosed up on this. Okay, so how would we get MC/DC coverage? So here we have three tests. Now again, I want to point out that it is not always going to be the case, at least as I understand it, that you're going to necessarily have more tests to get MCDC coverage than if you were trying to get simple decision condition coverage. Now let's go back and look at the code snippet again. If you've got a pencil or pen, you might want to write it down, because you can't see both of them at once. Okay, so it's A or B and C, right? All right, so we look at A, true. Well, first let's just evaluate condition coverage, okay? No. A, true, A, false. Okay, so we got condition coverage for A, and B, false, B, true. Okay, we've got condition coverage for B. C, true, C, false. Okay, we get condition coverage for C, okay? And we go A, true, B, false, C, true. That evaluates true, right? Because A or true or false is true. True and true is true, right? So we got that. And we have false or true. That's true. True and true is true. Okay. We say true or true. That's also true. True and false is false. So we got true, true, false. So we've got decision coverage as well. Okay. Now, has every variable independently influenced the outcome, the decision? So we look at test one. We say, okay, test one. If we changed A to false, we kept B and C as they are here, it would be false or false. False or false is false. False and true, that's false. That would change the decision. Okay, so A, we got A influenced the decision independently. So let's see, do we have, how about for B? Does B influence the decision independently? Okay, well for B, we look at this test, we get A or B, so false or true, that's true. True and true is true. Okay, so if we change B to be false, we'd say false or false, that would be false. False and true would be false. So B has changed, B has independently affected the decision there. And then finally, for test three, and by the way, this is a coincidence that each one is in a different test. I'll explain that in a minute later. So we say true or true, that's true, and false is false. If we changed C to be true, then the outcome here would be true, right? It would be true or true, which would be true, and then true and true, which would also be true. So the outcome would be true. Okay, so now a couple of points on this. One is the issue of coincidence, and then the second, more perhaps compelling question is the why question. Okay, so then the coincidence thing, I said it's just a coincidence that we have three separate tests, each one illustrating a situation where the control associated with a single variable is shown. It's just for illustrative technique. If you can identify any test where if one of the variables, if it took on a different value than it currently is in the test, that would change the outcome, then that variable is covered with respect to MCDC coverage. Even if that same test, there's another variable that you could identify where if you changed it, it would independently affect it. Okay, so it's not like a test can only be used for a single variable in terms of that independently affecting the outcome aspect of the coverage. It's just a coincidence that it worked that way here. And it also, of course, makes the example a little clearer. But I want to make sure you're not looking at this going, oh, well, it has to be separate tests. No, it doesn't. Now the bigger question is, well, wait, why does this matter? I mean, what are we looking for here? Well, what you're looking for is in a situation where, you think in your test that you know what values the different Boolean variables or logical relational expressions or so forth are going to take on. Actually, they don't. Actually, they take on a different value. And where you think something is true, it's actually false, or vice versa. Now, if that doesn't actually affect the control flow in your test, guess what? It can't affect the behavior of the code. And then you've got a bug. A value is being taken on that is unexpected to you, but you have no way of detecting that in your testing, right? Because when you're executing tests, if we're talking about tests from a point of view of dynamic tests, white box or black box, what we're doing is we're evaluating results, right? Something has to happen, and we compare that thing that happens against what we expected to happen, and we say, okay, well, that's right or not right. If you've got a bug and you don't design your test such that a control, in this case a condition bug, and you don't design your tests in a way such that each condition can independently affect what happens, and thus the behavior of the program, you really have no way of observing the outcome, and thus no way of knowing for sure whether the bug, or detecting the bug. Now, you've got no way of really seeing it. So that's the motivation here behind this, and why for safety critical code in airplanes, the FAA requires that you get that level of coverage. Okay, tough slog through Technicalville there, I know. But one last thing to mention here before we get into Q&A, something that you'll also potentially run into in code coverage metrics, and that is multiple condition coverage. And basically, this is where you say every possible combination of conditions. And in some cases, it means that can affect the outcome, and that can affect the outcome. And that refers to short-circuiting. So if you say if A and B, and A and B are both logical or Boolean variables, then there are four possible outcomes. It is true, 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 false, false, true, false, false. Now, if it's A and B, notice that through short-circuiting, you actually could say, well, there's true, true, there's true, false, but there's only false and doesn't matter, right? Because once you evaluate the first term in an and expression, then you, if it evaluates to false, then that's the end of it. The short-circuiting is going to stop it. So if you've got short-circuiting going on, and I think most compilers these days will, then you're not going to be able to test some of the combinations, or at least it's not going to be meaningful. You're going to have tests where you're creating multiple tests for a particular situation, but those tests don't result in any sort of different behaviors. So again, depending on whether you are doing short-circuiting, the derivation of the test is going to be a little bit different. But either you're going to generate all possible combinations, or you're going to sort of evaluate the short-circuiting, and you're going to generate those combinations that can actually affect the outcome. Now, so what you need to do if you're looking at this, and you got a tool, and the tool's giving you multiple condition coverage, you have to check whether the tool is doing that based on short-circuiting happening, or based on just the raw, Boolean truth table total number of tests that could exist. And then you have to sort of ask yourself, well, do I really need to run these other tests that can't affect the outcome. I mean, what exactly is the point of that? This is pretty rare that you're going to run into this, but you just should know that if you see multi-condition coverage or multiple condition coverage, then that's what they're talking about, is a complete set of conditions, complete set of condition combinations which might or might not be reduced by short-circuiting of the compiler. Okay, yeah, that's a lot of technical stuff in a short period, so appreciate you hanging in there. Hopefully that's been more clear than not. It is, for those of you with a programming background, this is not terribly complicated. If you do not have a programming background, it can be really difficult to understand these, because after all, what we are talking about here is what makes a program do one thing or another thing, right? And that's inherently has to do with how programs internally make control flow decisions, and that can be complicated. So in this webinar, what we've looked at is code coverage and the metrics and what's underlying them, the way in which those metrics are calculated, and hopefully they are much clearer to you. We've looked at various test techniques, behavior-based techniques, and so forth in previous webinars, and one of these the things to keep in mind about code coverage is, if you're doing black box testing, one of the things you might want to know, I think suggest that you really should want to know, is how thoroughly is my code exercising, or my test exercising the code. This is an interesting exercise to do. If you're doing this at the system test level, you run a check and see what percentage of the code is being executed by your black box test. I think you'll be surprised at how low that number is. Now, that might or might not be something that you want to confront at the system test level, but certainly for those of you involved in unit testing or helping people do unit testing, you really do want to make sure that these kind of techniques are being applied. And to the extent that at least statement and decision coverage are not being achieved at the unit test level, I think should all have a fair amount of skepticism about what level of confidence we can have in those tests. There's going to be stuff that's not tested. Now, some of these higher levels, like MCDC coverage, do you need to worry about that? Well, of course you do if you're in a regulated environment. But again, as I mentioned, there are bugs, logical bugs. By logical, I mean in the logic, in the Boolean decision making, that even if you get statement and decision coverage, they could get past you, but you would be able to detect them if you did modified condition decision coverage. So something to keep in mind, and if you're dealing with a really critical piece of code that's got some really complicated logic in it, then certainly there can be a reason to say, to have sufficient confidence in these tests, we really need to get that MCDC coverage. Okay, so as usual, I'll put the advertisement up. We'll get into the Q&A session. Presentation proper being complete. Submit any questions you've got via the question interface, and let me now undock that. Just a moment here. And another conference call kind of thing this morning on WebEx, and apologies to those of you who are on WebEx, but or work for WebEx, but it reinforced why I like GoToWebinar better, but still kind of clunky in that Q&A interface, but I've got it up here. Okay, we had a comment from somebody is asking, is there any way to increase the volume? No, I actually don't have a way of increasing volume on these, and I don't want to get too tied up in this. But if you did have some issues with the volume, let me know. There is a post on the RBCS blog page. It's from about a month ago from a fellow who had some audio issues. And if you did have audio issues and you can't find that out on the blog, let me know, and we'll forward you the link to that post and see if that helps. Let's see. And a couple of people commented they were not able to see the slides. Again, latest version of IE, you might have problems with that. So probably want to think about using another browser until GoToWebinar gets their Citrix more properly gets their problems with IE resolved. I did a blog post on that too. It's kind of surprising that the level of compatibility testing that does or doesn't go on. Okay, so Venkata asks, what is a good tool we can use for code coverage testing? Well, this depends. I mean, if you do not have any budget for this, then what you're going to want to do is look at the freeware options, of which there are many associated with typically the sort of the agile world. So, all sorts of add-ons for Hudson and so forth that do code coverage tracking. And then there are commercial tools that will do that. So, what I would do is say, like any sort of tool selection, what you want to do is first understand your requirements and constraints. I mean, are you doing this during system testing, or are you doing it during a unit test? Do you have a budget for this, or are you going to have to do this for free? Once you understand those constraints, you then should be able to do a web search, Google or Yahoo or something, and find a fairly substantial number of tools that will meet your basic requirements and constraints. And then at that point, you want to go through an evaluation process to select the one that you actually want to use. Nikos here is suggesting Eclipse. I'm not aware of that myself, but I would not be at all surprised if there's stuff that's that will plug in for that. So should be easy enough to check to see. I mean, if you just do a web search, Eclipse code coverage, you should be able to find information on that. Okay, let's see. Satish asks, is code coverage the right metric to measure the quality of QA tests? That is an excellent question, Satish. Thank you for asking that. It is a metric of the quality of your tests. It is a measure of the thoroughness of the tests with respect to the code. Now, let me point out something. You could get 100% statement coverage, decision coverage, and MCDC coverage, and get loop coverage at the 0 times 1 time and n times level, and still miss all sorts of bugs. And you might say, well, how could that be? Well, the way it could be is if the requirements are wrong, or if there are missing requirements, then guess what? There's code that's there that conforms to the requirement, but the requirement is wrong. So there's code that does the wrong thing because the requirements are wrong. Or in the case of missing requirements, there's just no code there. You don't want to look at this. What's the right word here? Not unilaterally, but you don't want to fixate on this alone. You don't want to say, oh, if my tests have gotten 100% statement, loop, decision, and MCDC coverage, then my tests are perfect and the system is perfect. No. This is one way of measuring how much confidence you should have in your tests. And there are other things that you do want to look at, like requirements coverage, or for the Agile world, user story coverage. You want to look at design coverage. If you support a lot of different configurations, you want to look at configuration combination coverage. If you're doing risk-based testing, you want to look at risk coverage. There are a number of different coverage measures, I guess I would say, and we're just talking about code coverage here. So be careful not to sort of overload code coverage with a whole bunch of meanings that it doesn't actually have. This is a very common mistake. So I'm really glad that you asked the question. Let's see. Okay, Steve says risk-based test coverage is really helpful. Thanks, Rex. Yeah, keep that in mind. If you're doing risk-based testing, that's what you're looking for, is appropriate coverage of all the risk items you've identified. Let's see. Paulo asked, do you know some tool for Java and .NET that helps choose the data for use in tests? So for example, if I have a method that should do calc A, B, but was implemented B, A, I will only know that it's incorrect if I choose the test data properly. Code coverage doesn't show me this. Yeah, that's another example. Code coverage can only tell you whether the code was or was not executed. It certainly cannot tell you whether the expected result of your test was properly defined. This is a problem that sometimes, or a mistake that sometimes people make. There's this issue of, if you're not familiar with this term, what's called the test oracle. And basically the test oracle is the thing that you refer to determine whether the test, the result of the test is correct or incorrect. It can be requirements, it can be design. It can be any number of things, but it cannot be the code itself. The code itself cannot tell you what the correct result is, because if you base your definition of the correct result of the test on the code itself, you're just testing that the compiler works. You're testing that the compiler does what it says it does. Now, if you're testing the compiler, that's all well and good, but assuming you're testing the application itself, then you need something other than the code to which you can refer to define the expected results. There are some test design tools out there that say that they will help you work through this process of selecting the data and defining the test result. But just with all due respect to the people involved, and I know some people have been involved in creating such tools, and their heart's in the right place, but I've never seen one that actually did a decent job of solving this oracle problem automatically. Ultimately, this question of, what's supposed to happen when I do X is something that the tester has to figure out. Let's see. Other questions here. Srinivas asks, as I understand, these techniques are used to write as few test cases as possible and cover more code. Well, I think the way that I would put it, Sri, is that what I want to do is use code coverage techniques as a measure of the thoroughness of my tests. And when the code coverage techniques reveal things that haven't been tested, either statements or decisions or the MC/DC world conditions that haven't had a chance to influence an outcome, whatever those things are. When code coverage reveals things that are not tested, and I look at those and say, we really should test that, I'm going to add a test. You don't want the code coverage metrics to become like sort of a god or something, and you say, oh, we absolutely have to do this. I mean, you want to be flexible and say, there can be circumstances where we're going to get less than 100% coverage in certain areas. Like I mentioned, the example of 100% statement coverage. It sounds like a good goal, and it seems like that should be a general goal, but you have to understand there can be situations like exception handlers, or it would be very, very difficult to create the exception where you might not be able to get to that level of coverage, and that might be okay. So in terms of like minimizing tests, well, yeah, I mean, yeah, we always want to do that, because this is the central one of the central problems of testing, is that there are an infinite number of tests that we could run, and we're not going to run an infinite number of tests. So there's a selection issue, right? So we're always selecting, and that comes back to, again, you don't just say, well, we have to get to X level of statement coverage or decision coverage or whatever in some arbitrary fashion, because that might or might not be appropriate. Let's see. So Anthony has puts up this expression here. I'm going to see if there's a way that I can show this. Let's see, paste. I'm not sure I'm going to be able to show this. So let me read this out here. And you've got a paper or pencil or pen, and I'm going to write it down. So this goes open parens, A or B, close parens, and C equals D, close parens, close parens. A or B is one condition. Is that an atomic condition or not? Okay, so what are the atomic conditions there? If we have A or B and C equal D. So basically, let's assume that, Anthony, that A is a Boolean variable, takes on a true or false value, and B is a Boolean variable, takes on a true or false value. So A is an atomic condition, and B is an atomic condition. Now, C equals D, where the equals is the relational operator equals. Let's assume that C and D are both integers. Then in that case, C equals D is the third atomic condition there. So basically, when you're looking at an expression such as A or B, if we can break that down into pieces where those pieces have a true or false value, then those pieces are the atomic conditions, not the overall expression. So A or B is not an atomic condition, because we can break that down into A and along with B, each of which evaluates independently to true or false. C equal D is not that way, because C is an integer and D is an integer, so they don't have true or false value. Now, for those of you with a C programming background or C++ programming background, you might say, well, wait a minute, I mean, I understand how logical evaluation works in C, and I actually could assign a true or false value to C and to D based on whether they're equal to 0 or not. But that's not what's meant here. Okay, that's now you're getting into the implementation of the language. So I hope that helps clear that up. Let's see, other questions. I got a bunch of them here, so I want to make sure I plow through them. Let's see. What we got? Kelly asks, hi, if this webinar is recorded, is it possible to send me the link so that I can review it because I missed the beginning? Thanks. Yes, the webinars are recorded, and the recordings are posted on the RBCS Digital Library, usually within 2 or 3 days of the webinar itself. So what you want to do is come back to the rbcs-us.com website and go to the Resources tab and then navigate to the Digital Library, and you will find the recorded webinar there. Anne asks, please explain the term atomic condition. So I just went through that example from Anthony, which I hope helps, but just to define it, an atomic condition is, well, atomic, as you know, means something that cannot be further subdivided, right? Basically, it means that the atomic condition is you're looking at an expression or a variable or something like that where that expression or variable evaluates to true or false. And if you tried to break it down any further, either you couldn't break it down any further, or the constituent parts that you would break it down into would not evaluate to true or false. They would be strings or integers or floating point values or something other than a logical variable. Ken asks, are there tools that analyze code and emit or highlight the lines that are required for MCDC test generation? Yes, there are. And some of our clients in the safety critical world have used them. I'm not familiar with the names, but this is easy enough to find on the web. Find code coverage tools, and then when you're evaluating their capabilities, if you want to have MCDC coverage capability, just look for that. Let's see, somebody asked here, can you be said to accomplish any measure of code coverage if you are never given the code to look at, but instead must simply exercise options that you see in the GUI? And the reason I said somebody asked the question is because a person entered their ID as XXXX. So I'm happy to answer your questions by your actual name, but if you don't give me your actual name, I really can't. Anyway, so back to this question, can you accomplish any code coverage measurements if you're not given the code to look at? No, that would not be possible. In order to do this, in order to measure code coverage, you do have to have access to the code, because what you're going to do, you're going to produce a special version of the test object, the software under test, using the code coverage tool. Now, typically the way this works is that you run what's called an instrumenter on the code, and it inserts special statements into the code that are supposed to be as unobtrusive as possible. And then those pieces of code, those instrumentation pieces of code, as you're running your tests, make entries into a table. Then you have an analysis tool that after you run your tests, you're able to look at the results of the analysis, and that's going to tell you what levels of coverage have or haven't been achieved. And in fact, most of these tools are going to actually allow you to browse the code and identify untested statements, untested decisions, untested conditions, and so forth. But you do have to have the code. Venkata asks, is code coverage done primarily by developers during unit testing or testers after it reaches the test cycle? You can, Venkata, use code coverage during system testing to get a measure of how thoroughly your tests are covering the code. Now, that is often a very eye-opening experience. Most people who've done this at the system level find that like 20 to 25% of the code is tested, 20 to 25% of the statements. Now, is that a problem? Well, it depends on what you haven't tested. But usually, achieving a high level of white box test coverage during system testing is not the goal. The goal is going to be that at the unit level, as you mentioned, the developers are going to try to thoroughly exercise the constituent code itself, so that when we get into these higher levels of testing, we can focus on the behavior of the system. But if thorough unit testing has not occurred, then you sort of have a problem here, because it's quite possible that you're going to go into production with code that has not been tested at all, pieces of code and statements that have not been run, decisions that have not been tried out, both true and false, loops that haven't been exercised, and that's, you're going to then get you're going to have a lot of bugs get past you. So it really, it is important that at the unit level that this appropriate levels of coverage be achieved, and also that you as a tester, if that's your role, you're running independent tests, be able to have an intelligent conversation with programmers about the level of unit testing they did and how confident they are in terms of their coverage. So Janet is asking, can you show the metrics again? Well, what I would ask Janet is that you go back through the presentation, and if you want to re-review the different metrics we talked about, or listen to the recorded version of it. If you've got a specific question about a specific metric, just go ahead and send it to me, and we'll go back to that specific metric. Shri asks, what's the difference between decision and condition coverage? Okay, so let's go back. Let's go back to that. Just out of the way there. Okay, so condition coverage. All we're saying in condition coverage is that every atomic condition has to have been exercised once true and once false. So again, this is, you got to identify the atomic conditions, and then you've got to make sure that in your tests every atomic condition has been true at least once and false at least once. Now that will not necessarily give you decision coverage. Decision coverage means that the overall outcome has been at least once true and at least once false. So let's take a look at this guy here. We have D and F. Okay? So there are two atomic conditions, D and F. So I could get condition coverage by testing with D true and F false, and then then D false and F true. Okay? Notice that D has been true and false, and F has been true and false. But there's your problem with that. If D has been true and F is false, and F is true and D is false, that D and F every time has evaluated to false. So we have not tested the decisions, even though we have tested the conditions. So I hope that makes that a little bit more clear. Let's see. Lily says, I cannot see the other's questions, such as the current expression in discussion. Yes, that is a problem. I could not find a way to display that Anthony's question while I was discussing it. I apologize for that, but couldn't spend 5 minutes trying to navigate through GoToWebinar's capabilities while you guys were all on the line. Ken says it's unfair to call wrong or missing requirements bugs because it is not the developer's responsibility to do other than code to spec. Conscientious developers might feed back questions on specifications but should not unilaterally take on fixing specifications. Okay, let me see. How do I want to reply to that? I don't think it's unfair to call them bugs, Ken, but I think it would be unfair to call them bugs in the code. They are not bugs in the code. They are bugs in the requirements. If the requirements are incorrect, then that's a bug. Now, certainly I could not expect necessarily that the programmer would know better than the business analyst or requirements engineer who came up with the requirement. So yes, I mean it's fair to say that if the programmer is given a flawed requirement or user story or whatever, they're given bad information about what they should build, then what they're going to build, even if they build it perfectly, will be bad. Now that's not their fault. That's not, and I think this is this is something we have to be really careful of in the use of the word like bug or defect or something like that, is that this is not about fault. And in fact, some people use the word fault or use fault as a synonym for bug or defect. I've avoided that specifically because when you start talking about faults, it sounds like you're talking about something that is someone's fault. And that's just really counterproductive. I mean, generally, what you're looking at when you're looking at defects, bugs, call them what you want, is you're looking at manifestations of process capability or lack thereof, basically. So if the requirements process is broken, however, whether you're agile or following a more traditional life cycle model, doesn't matter. If your requirement specification process is broken, you're going to get a lot of bugs introduced in the requirements, and those are going to then ripple through into the code and then be either code that's missing or code that has the behavior that is as specified but which is wrong, and that thus is a bug. And again, that's a process capability thing. You know, I think it's a problem in our industry that leads to all sorts of evils that we assume that bug equals bad programmer. And I'm sorry if it sounds like I'm picking on you, Ken. I'm not. It's just that we've run into this with a number of clients, and you know, really need to think about, you know, when you're looking at a bug or you're looking at a collection of bugs, what those are telling you about is more often than not the capability of your software development process, not your people. That you know, the bugs are the manifestation of a process breakdown. Sri says, thanks for going back and explaining the difference between decision and condition coverage. So I guess that's clear now, Sri. Thank you for that. Let's see. Anthony says, since some scenarios can slip through with decision condition coverage, would statement be the better choice since it would cover the statements in all flows? Well, no. Actually, decision condition coverage, if you get decision coverage, you should get statement coverage, as long as you're careful to exercise every entry point and exit point in the code. In other words, there's no functions or other like exception handlers or anything that have not been executed. Now, it's sort of I could say distinction without a difference, but it's kind of like that in the sense that if you're using a code coverage tool, pretty much all of them are going to give you statement coverage. In some cases, they're going to call it instruction coverage. In some cases, they're going to call it code coverage. In some cases, they'll call it statement coverage. But pretty much all of them are going to do that because that's the easiest one to do. And most of them are also going to be able to do decision coverage for you. So you're going to be able to find pretty quickly whether you're getting 100% decision coverage and 100% statement coverage. And to the extent that you don't have 100% coverage in either of those areas, the tools will generally highlight for you fairly quickly what you're missing. Now, condition coverage, some of the tools might give you that, some of them might not. If you decide that you want to look at that as well, then make that one of the requirements in your the tools that you look for. Let's see. David asks, what are some target metrics when using coverage tools? If we can't get 100% decision coverage, is 70% a typical number? Well, I don't know. We've seen this with clients. I hate to just throw out a number and say, well, you should get this. I think it's fair to say that during unit testing, what you would want to see is at least 100% statement coverage, because if you don't get that, then that means that somebody has written code that has never been exercised, which it could contain a surprise, and so I think that's kind of fair to say. Though again, you can posit scenarios where there's something that just can't be reached for whatever reason. Decision coverage, likewise. I think it's good unit testing should result in every decision being taken both true and false. Now you start to get up to the higher levels, like MC/DC coverage and so forth, and I mean, I guess you could make a case that that's not 100% necessary, but you know, a lot of times the code has fairly simple conditions in it, and getting just decision coverage will actually get you to MC/DC coverage as well, because you've got very simple conditions. If you have complex conditions, or you would have to actually add more tests, well, that's sort of all the more reason to get to MC/DC coverage, because that's a situation that could break where it's complex. But I don't want to throw out numbers and say, you know, that all code should be tested to this level or something, because it's just too easy to come up with a hypothetical scenario where that rule breaks down. So, you know, I don't want to be prescriptive about that, but you know, think about it, and you know, there are these levels of coverage have been defined because there are bugs that have been observed that are associated with not getting to those levels of coverage. So Ken's got a reply here, which I want to read real quickly to what I said with respect to requirements. He says, exactly, this is why I call coding errors bugs and allow them to get into the bug tracking system for repair by developer. Finding another process for reporting requirements / specs problems and converting those into new or revised code specs is something else. And B, I consider developer sanity maintenance a big part of my job. Okay, fair enough, Ken. Though let me just point this out: that if you track defects in work products other than code in a different repository, one of the things that can happen, and we've seen this happen with clients, is that it's very difficult to come up with metrics on what percentage of defects are introduced at what point in the process. So there really is a strong case for using a single tracking tool. Now, it's tricky because obviously the information that you need to gather on a requirements defect is different than the information that you need to gather on a code defect, and you have to be careful with how you implement this. But it's really important that you be able to look at the software process in terms of its defect capability and understand what's really going on. And without that common repository, it's very hard to do that. Okay, so that's got a lot of great questions. Once again, more than I had time for. Something to remember about this is that we're always looking for blog ideas. So if you send an email to info@rbcs-us.com, you want to post a follow-up question, I'll try to get to it and answer it on my blog in the next few days, so we can continue the discussion and conversation there if there's anything that I missed. To close this session, we'll tell you a little bit more about the resources that we offer. These webinars are run free once a month. Check our website, rbcs-us.com, to sign up. If you want a special webinar presentation for your company only of this webinar or any other topic related to software testing, you can contact us at info@rbcs-us.com or via our website. If you don't already receive our regular free newsletter, you can sign up at rbcs-us.com. By signing up, you'll get valuable discounts on consulting and training services, along with a regular newsletter that includes a featured article and a featured article on software testing and quality, and news about what RBCS partners are doing lately. You can follow us on Twitter. We are at RBCS, or twitter.com/RBCS. And we're on Facebook too, facebook.com/pages/RBCS-INC. Do remember to check your email over the next couple days. You might be the lucky winner of a free e-learning course from RBCS. Your attendance registered you for that drawing, which will happen shortly. Check out my blog. That's rbcs-us.com/blog. Post comments or email me about topics that you'd like to discuss. Check out the digital library that has recordings of these webinars along with podcasts and videos. Subscribe to our podcast via iTunes by entering RBCS Podcast into the search string, or see the videos and recorded podcasts by subscribing to the RBCS channel on YouTube. We offer these free resources as a service to the software testing community because at RBCS we're a not-just-for-profit company. This concludes the webinar. I'd like to thank everyone for joining us today and hope to see you at future webinar events.